Questions?
Do you post the answers somewhere?
The solutions?
Yeah.
I wasn't planning on it, but I guess I could. Okay, so let's see. I guess it more or less the grading went kind of the following way. You got obviously 4 points for the first problem in the sense that it's just finding the domain. One popular choice was that the domain is from 4 to plus infinity, which I don't necessarily understand why, but I mean I do understand why, but I want to just probably say a few words about it. Remember when we talked about functions and domains of functions, I told you, and I said it repeatedly, that one of the things you want to make sure you do is you actually just write exactly what you're looking for and work out the algebra. You don't have to just look at it and try and guess the solution, which is probably why some of you ended up with 4 to plus infinity, because you just looked at it and tried to eyeball it. So the first square root says x has to be bigger than or equal to 0, right? We can't have negative numbers inside square roots. Well, the same follows for here. So 4 minus x has to be bigger than or equal to 0. Now if I am to actually solve this particular inequality, this just says that x is less than or equal to 4. Right? Or if you prefer, minus x is bigger than or equal to minus 4. And then if you want to get rid of the minus, the inequality sign changes. Right? Everybody understands this? Yeah?
Yeah.
Wonderful.
Got it.
And so the domain then is obviously going to be 0 to 4, because the first one is from 0 to plus infinity, the next one is actually from minus infinity to 4. Right? Do I need to draw a graph, or is this clear?
Clear.
Okay. For number 2, problem was worth 8 points. You got 4 points if you completed the composition of functions, and you got another 4 points if you actually wrote the domain. A very popular choice for the domain was that because sine of x is defined everywhere, the domain was all real numbers. That seemed to be the most popular and most frequent answer, which is wrong. So if you look at number 2, g of f of x was equal to 1 minus the square root of sine of x. And I tried to give you a hint in the sense that you have to think about the graph of sine of x. What do we need to know? Well, we need to know that sine of x has to be bigger than or equal to 0, right? So as a consequence, this is my graph. What do I have to focus on? The part in which sine is positive, which would make x be in 0 to pi. Right? Does that make sense? And you're looking at a periodic function of period 2 pi, so it'll be 0 to pi, and then it'll be 2 pi to 3 pi, 4 pi to 5 pi, and so forth. I would be more or less happy with just some variation on this. Some of you got the solution, and then when they tried to generalize it, you didn't generalize it in a correct way. I didn't take points off for that because I figured you at least know what you're looking at, even though you didn't write it correctly. So I tried to explain why you didn't get it right. But anyway, does this make sense? And some of you actually, I guess, mistakenly drew the graph of cosine instead of sine, so you had minus pi over 2 to pi over 2. Or some variation of that. But the most popular 2 answers were either minus infinity to plus infinity or 0 to plus infinity. Those are usually the 2 most popular answers. Okay. How much time have I spent on negative numbers coming out of absolute values? I actually counted. More than half the class among those of you who actually attempted problem number 3, said that the absolute value of 7 minus 3x plus 5, which equals 12 minus 3x, which equals the absolute value of negative 3 times x minus 4, is less than epsilon. Therefore, the absolute value of x minus 4 is less than epsilon over negative 3.
Wait, is that the right answer?
No. And I think I gave half the points if you actually did this, even though inside of me screamed that I should just cross everything with red and just say no with capital letters, considering how much time have I spent talking about the fact that when you take out numbers out of absolute values, they always come out positive. Number one, and moreover, if you look from here and you say that minus 3 times the absolute value of x minus 4 is less than epsilon, which is in itself wrong as wrong can be, how can you get from here to here? Because when you're multiplying by a negative number, you're changing the sign of the inequality. So there's actually two things that are wrong to it. First of all, you can't have a negative number coming out of the absolute value. Second of all, if you divide by that number, your inequality will change. Is everybody understanding this? Did I not spend about 45 minutes talking about this?
No, it paid off. I got it right.
Okay, he's got it right. 20 other people didn't, at least. Does this make sense?
No negatives.
Yes? Okay, so clearly that's not what you want, right? Okay. And now we come to my favorite problem. My favorite problem in the sense that I gave, again, I forgot to count the number of exams, and I probably should have done that, because in this case it was actually an overwhelming majority. Problem number 4 said you have two functions, f of x equals x squared plus x minus 6 divided by x minus 2, and g of x is equal to x plus 3. And part A asked to explain if f of x is equal to g of x. Now in itself, the fact that I'm asking you that particular question, your immediate answer should probably be no, in the sense that why would I bother to ask you if it's so obvious that it is yes? I'm just pointing it out. But more importantly, how much time have we spent on these types of functions when we looked at limits and we said we can graph this and it's going to have a hole at x equals to 2. Since it has a hole at x equals to 2, it can't equal g of x. Is everybody understanding this? I mean, when we talked about limits of this nature, we talked about the fact that the limit will actually end up being 5, which is part B, but the bigger issue is the fact that the function is not even defined at that point because it has a hole, right? That's actually the key idea. And the way I usually wrote it was the fact that this is equal to x minus 2 times x plus 3 divided by x minus 2. And now you can cross out the x minus 2's with the understanding that x cannot equal 2. You can't cross out the zeros, so you have to make sure that that's taken out of the equation. And so part B, pretty much every single person in the class got right. But anyway, if you're wondering how the distribution of points was, it was 5 points for part A and 3 points for part B, and every single person that said yes on the first part, I gave you 2 out of 5, even though I should have probably given you 0 out of 5, because at least you attempted to write, and some of you gave me a whole long story about how things cancel, and when they cancel you end up with x plus 3, which is the same as g of x. So I figured if you put all that effort into writing all of that, at least you wasted all that lead, I might as well give you something. So, is this making sense? Okay. Questions about this or move on? Okay. Number 5. Is there any point in talking about part A?
No.
Okay. Part B.
Yeah, what was the answer?
Oh, actually, I did that on Friday. That's right. The answer was a half. The one thing I should point out, and this is actually, because I've seen this on part A for some of you, and even on part B. The only times where you can actually, and this is one of the reasons why sometimes I'm reluctant to give you cheat sheets, to give you ways of actually cheating the system without actually computing things. I said, at some point I said, if you look at, if you have a polynomial divided by a polynomial, you look at the largest degree and you look at the ratio between them. That only works if you talk about infinity. If you talk about any other limit to any other number, that doesn't work. The only reason why it works at infinity is because the leading term will be the one that decides everything, because it's the largest term. If you go to any other number but infinity, it won't work. Okay? Oh, yeah. The other thing, which made my hair raise up. The square root of 9x squared plus 1 is not equal under any circumstances to 3x plus 1.
Oh, wait, where do we get this 3x?
Well, the idea is the square root of a squared plus b squared does not equal a plus b.
What have you been?
Do you understand why? And for those of you, I don't remember if I actually did it for every single person, but considering I started saying this more and more frequently, I actually started saying, when in doubt, you know, when you think you're really being creative with the mathematics, okay? Because the key idea is, if this in fact would be equal, then your limit would be basically very, very simple and very short. Well, guess what? Chances are that's not going to happen. So, if you really find yourself that the problem is really simple, chances are you were creative with inventing some mathematics that doesn't exist. So, is the square root of 1 plus 1 equal to 1 plus 1?
No.
Left side says square root of 2. Right side says 2. Square root of 2 is clearly not equal to 2, right? Everybody understands this? When in doubt, put in some numbers, see if it works. If it doesn't work, then chances are you just, you know, try to invent some new techniques. Is this making sense? Yeah? Funny part is, and this is kind of like the irony of this particular problem, is that if you did write this, you were actually quite close to the answer, because the answer was minus 1/3, and most of you who actually did this ended up with 1/3 because you looked at the ratio of coefficients and boom, it works. But that's just because I guess it worked for this particular problem.
Could you show us how to do this problem? Yeah. This is messed up so bad.
Well, you know, except for the minus, this was a homework problem, right?
Yeah, it was. I had a long discussion with someone about it.
The limit as x goes to minus infinity of x plus 2 divided by the square root of 9x squared plus 1. So the idea is that I have x times the factor 1 plus 2 over x divided by the absolute value of x times the square root of 9 plus 1 over x squared. Right?
Yep.
I did 2 steps into one. Right? Remember, first of all, I factored out an x squared inside the square root. And then when you take it out, you end up with absolute value of x. Now, because I'm going to minus infinity, this becomes the limit as x goes to minus infinity of x times 1 plus 2 over x divided by minus x times the square root of 9 plus 1 over x squared. And now the x is cross out, and so we're left with 1 over minus the square root of 9, which is minus 1/3. Does that make sense?
Oh, wait. Does negative infinity cancel out the x and 2 over x?
Again, when x goes to infinity, any number divided by x to any power is going to be 0. Because this is 2 over infinity, which is 0. Then this is also 1 over infinity, which is 0. So they both go to 0. Yes?
So you have the absolute value of x, and you plug the negative infinity into
Because x goes to minus infinity, the absolute value of x is negative x. The absolute value of x is defined to be minus x if x is less than or equal to 0, or x if x is bigger than 0. So since x goes to minus infinity, it's clearly negative, and so your absolute value becomes minus x. Okay? Alright, and now we come to number 6. Which I did in class about a week before the quiz, or not even a week before the quiz, like 2 days before the quiz or something like that, right? And I went through the whole story of what you're actually supposed to do, right? You're supposed to look at from minus infinity to 1, and then you look from 1 to plus infinity. And the idea is from minus infinity to 1, you're looking at x squared. That's a polynomial. They're continuous everywhere, so it's going to be continuous in that interval. Similarly, you look at the square root of x. It's continuous on actually from 0 to plus infinity, so it's clearly going to be continuous from 1 to plus infinity. Now, it's not suffice to say that square root of x is, and I've seen this on some exams, it's not suffice to say that the square root of x is continuous from. So the idea is the following. F of x is equal to x squared for x being less than 1, and the square root of x for x being bigger than or equal to 1. Well, since you look at x squared, clearly this is going to be continuous on minus infinity to 1. Moreover, I can say that the square root of x is in fact continuous on closed at 1 to positive infinity. Even if you put these together, you end up with the entire real line. That's not sufficient to say that's the case, because that just means that you have a function that comes with a hole, and then you have another function that comes with a dot goes that way. We have to also talk about 1 to basically talk about the fact that those 2 points are the same. Does that make sense? Now, some of you just drew me a graph. I told you the graph is not acceptable. Why is it not acceptable? Well, because I was actually nice enough to give you a nice function. Okay? How about if I would give you a function of the nature of, I don't know, x cubed plus 3x squared plus 2x minus 5, as x being less than 1, and the square root of 3x squared plus 2x, let's see, minus 4. Now what? Skip it. Do you understand why graph is not allowed? We're not talking about graphically. We talked about the fact that functions are continuous. Graphically speaking, they're continuous because, like graphically speaking, they're continuous if the line is uninterrupted, right? But we said that's such a vague general description, and so what we really are looking for is the algebraic property of when a function is continuous. Now, again, one of the reasons why we put such a stress on this is the fact that, for instance, today we're going to learn about derivatives. And we're going to learn that a function has a derivative if it is continuous. Now, if the function is ugly enough, how do you know if the function is continuous? Do you really spend the time to graph it to make sure it's continuous or not? Or do you use some algebraic properties of it to realize that it's continuous? Is everybody understanding this? Yes?
Yes.
Okay. And this quiz, definitely next time I'm teaching Calc 1, that's the function I'm putting for continuous.
So,
Yes.
So for an answer, you want us to show the domains of know.
Not the domains. The domains are a good start, but you also have to state the fact that the domain is that doesn't necessarily mean anything. You have to state the fact that you know that polynomials are continuous on their entire domain, rationals are continuous on their domain, trigonometric functions are continuous on their domain. So, fine, getting the domain is good, but you also have to state the fact that it's continuous there because it's one of these types of functions. Again, we haven't talked about all the functions. If I throw an exponential at you, or if I throw a hyperbolic trigonometric function, do you know that the function is going to be continuous on its domain? You don't at that point, right? We haven't actually learned the tools about that.
Okay, so you want to show the domain and then explain why. Give me examples.
Again, I did this problem step by step, exactly this problem, about a week ago. So, if you don't remember, or if you took sloppy notes or anything else, remember, this is an online course. You can find this in the class notes. Okay. Any other questions? The average was about 64%, if that's what you're... Okay. Do you have any questions about Friday's lecture? And I know it's been a long time. We're talking about derivatives. Yes?
I have a question on number 16 of the homework.
Number 16? Okay. What would be your question?
How do we solve that, basically? It gives us the information but no equations, and we're supposed to find the equation.
Well, that's the point. You just have to remember what the equation of a tangent line looks like. So, equation of a tangent line at the point A and f of A is given by, do you remember what it is? Y minus f of A is equal to m times x minus a, right? But we found out later on that m is nothing else but f prime of a. Right? So if you look at 16a, you're basically given a, f of a, and f prime of a. So all you have to do is just put each one in its spot, and you get your answer. That's basically the whole reason. The reason why I gave you this problem, it's not a hard problem, it's just kind of like basically seeing the information in front of you without actually going back to computing the derivative and all that. Does that make sense?
Yeah.
Part B is going to be just a little bit of algebra. So for part B, it's a little different because it says the tangent line to the point 4 and 3 passes through the point 0 and 2. Find f of 4 and f prime of 4. I don't know why they ask you for f of 4. The tangent passes through the point 4 and 3. What's f of 4? 3. Right? So the only thing you have to figure out is the slope. And guess what? You're given 2 points. So what's the slope? Rise over the run. Again, these are not hard problems. It's just kind of like trying to make you think what exactly goes where. Okay? And again, this is again one of those situations in which what we really prefer is the point slope form and not the slope intercept form. Notice how things always show up a lot easier in this form versus the slope intercept. Because the intercept has nothing to do with a particular graph, it just happens to be where the line crosses the y-axis, while there's really no bearing on your original graph where the line crosses the y-axis. Versus the actual point will be on the graph of the function, so it plays a double role. Is everybody understanding this? Okay. What else? Yes.
Number 30.
Number 30.
Yeah, I just didn't understand exactly what they're asking.
You're supposed to figure out what the function is and what the value of a is.
That's it?
So, eyeballing it, what do you think the function is?
Well, it has to be.
Or better yet, let's start off in a simpler fashion. What would you guess a to be?
Or F base.
So we have the limit as h goes to 0 of the fourth root of 16 minus h minus 2 divided by h. Right? So what should we identify right off the bat? Remember, the limit as h goes to 0 of f of a plus h minus f of a divided by h. This is the form of the derivative, right? What should we easily identify? F of a is equal to 2, right? What else can you identify? Well, we can identify that f of a plus h is the fourth root of 16 minus h, right? So what is a? (16) and the fourth root of x. Does that make sense? If you look here, you see that f of a plus h is the fourth root of that stuff. So that in itself should be an indication that f has to be the fourth root of something, right? Now when you look at f of a, that's just 2. Well, the fourth root of 16 happens to be 2. So it only makes sense that it's in this fashion. Do you understand? And that's what you have to do for the, I guess I skipped 32, didn't I? I don't think I gave it to you as a homework problem because it was just too simple, I think. Okay, so let's see. Just be careful with 34. You can clearly identify what a is, right?
Yes.
What is a?
No?
What form of the derivative is 34? The limit as x goes to a of f of x minus f of a divided by x minus a. So a is 1. And so you have to identify what the f of a is, or what f of x is. And I know the idea would be to assume it's t to the fourth plus t, or t to the fourth plus t minus 2, or something like that. But just keep in mind that whatever you choose for f of t to be, f of a, or f of t minus f of a has to give you that original function. And f of a is going to be, whatever the value is, right? Okay. So, the derivative of a function f of x is given by f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of a minus f of x divided by h. So this is section 2.2. Section 2.1, what we talked about was the fact that the derivative of a function at a particular point was given by this expression with a's instead of x's, right? And so the idea is, if you define that for every single value of a, then you can define the derivative as an actual function, okay? And geometrically, one way of thinking about that is, you can just think about the fact that the derivative is going to be the slope of the tangent line at any given point, okay? Remark. The domain. So clearly, defining it in this fashion is going to give us a function, right? So the domain of the derivative f prime how should I phrase this? Will be a part or all of the domain of f. So what I'm basically trying to say is that the domain of f prime cannot be larger than the domain of f, number one. Does that make sense? Is everybody understanding why? I'm defining it to be a limit in terms of f, which means f of x has to make sense to talk about f prime of x, right? So it can't be larger, but it doesn't necessarily have to be the same size as f, okay? Best example that I can give you, f of x is equal to the absolute value of x. So let's do the following thing. Find the domain of f, find f prime of x, and find the domain of f prime. Or maybe I should hold off on the f prime. I guess I don't have to. It's simple enough to solve. So what is the domain of f? Everything? Right? Okay, how can we handle the derivative of f? Should we talk about it geometrically? Let's talk about it geometrically. What is the graph of f? Everybody knows this one. A v. Right? So f prime of x is what when x is less than 0? Negative 1 and positive 1. Do you understand why? Well, as it turns out, if it's a linear function, the tangent is the function itself. Right? We define geometrically, we define the derivative to be the slope of the tangent at any given point, right? Pick a point. How would the tangent look like? It's going to be the line itself, right? Since it's the line itself, it'll have a slope of -1, right? Similarly, think about f on this side. The derivative will have a slope of 1. Does that make sense? What can we say about 0? That's where the derivative doesn't exist. We actually, why doesn't it exist? Well, think about coming from the left to 0, your slope is -1, right? Coming from the right, your slope is 1. They're not going to have the same slope at 0. This is called, and we're going to talk about this in about a couple of minutes or so, this is called a cusp. The idea is it's a sharp turn, and so the function is not going to be not going to have a derivative over there. And so what is the domain of f prime? minus infinity to 0, 0 to plus infinity. Does this make sense? Yeah? Right? Does this make sense? Let me see. Yes.
The derivative, think of like an imaginary line that just crosses the axis once.
Sorry?
Like, what are we saying here? Like, what the derivative is? Are we talking about the tangent line that only goes through the function once?
Yes, that's how we define the derivative, the slope of the tangent line. Right, that was the first definition. We also defined it to be the instantaneous rate of change. Right? But graphically speaking, if you think about it as the tangent of the slope, the slope of the tangent, then you can see it clearly, clearer. Okay? Does that make sense? Okay. Notations. And I'm going to list a few of them here, but we're going to end up using a couple of them. So f prime of x, we can write it as y prime, which is not necessarily that used, or I don't necessarily prefer it, and I'll explain later on why. You can also write it as dy over dx. We can write it as df over dx. We can write it as d over dx of f of x. We can write it as capital D f of x, or we can write it as capital D with a little x f of x. Enough definitions? The ones we're going to be currently using are f prime of x, dy over dx, and probably d over dx of f of x. This particular notation, dy over dx, is called a Leibniz notation. And whenever you're home and trying to figure out derivatives and you can't get them, you can blame him. He's the discoverer of derivatives. Hence, that notation is given, his name, because and I guess they have a whole story about him here, if you're curious, on page 87. Write a 300 word essay about what you read. No, I'm joking. Okay, so does this make sense? Why is this notation making sense? Why is this even used, or why is this used? Well, later on this semester we're going to start talking about something called implicit differentiation. And what implicit differentiation does is, what happens if I can't actually write it as a function of x? So what happens if I can't actually come up with a function that says y equals f of x? Can you give me a very simple example of that? Think about x squared plus y squared is equal to 4. How about if I look at this point right here, and I'm asking you to find the equation of the tangent line? Well, I need a derivative, right? But I don't actually have a function. I have an equation, right? Everybody understands this is not a function, right? It doesn't pass the vertical line test. One way of going around this is to actually split this up into two parts, define this as a square root of 4 minus x squared, define that as minus the square root of 4 minus x squared, and proceed in that fashion. but trying to take the derivative of that and everything else is going to be much messier. We're going to talk about, I probably shouldn't spend too much time on this because we have a whole section in the book called implicit differentiation, so we're going to come back to that later on. But the idea is sometimes we don't actually have it written as a function, so it's very nice to actually have it in this fashion. I also like this many times because I don't necessarily have to define a function. So for instance, if I say, what is d over dx of x squared plus 2x minus 1? What I'm basically saying is, I have my function x squared plus 2x minus 1. What is its derivative? And so in this fashion, you can write it directly a lot simpler instead of actually defining it as a function, writing f prime, and so forth. Is that making sense? The last two notations I will never use. If you're used to any like CAS algebra systems, I guess that's CAS stands for computer algebra systems. So I basically just said it twice. The name might not necessarily say anything to you, but that just means Maple, MATLAB, Mathematica, all these computer tools that help you with math. They're very useful, so I don't know how many of you actually ever used them. But there, if you actually ask for a derivative, capital D is usually the letter to use. Okay. Now, you called me, you heard me say, another definition that another thing that I'm actually going to use quite a lot at some point is the following. If I want to say f prime of 2, okay, and I don't actually have a function written, this is the same thing as saying dx over dy, a vertical bar, x is equal to 2. Does this make sense?
Is it dy? You said dx over dy.
I said, oh sorry, dy over dx. Does this make sense? Well, you're evaluating just at that point. You're thinking about integrals. This is just one you're evaluating at this particular point. It's exactly the same thing as saying take the derivative, put in 2. That's basically what we're saying. Take the derivative, put in 2. Okay? Alright. I said a few times differentiable function, and I didn't actually say define what that is. So definition. A function f is differentiable at a number a if f prime of a exists. And so a function is differentiable means, does it have a derivative? That's plain and simple what it means. Okay? Let's see. It is differentiable on an interval, on an open interval, I should say, if it is differentiable at every point in the interval. Okay? So now, theorem. This is a very useful theorem for us, but you have to be careful how you apply it. If f is differentiable at a, then f is continuous at a. So as I said, this theorem is very helpful as long as you're very careful on how you apply it. What I wrote I don't know, did I write it big enough? The converse is not true, which says if a function is continuous, it may not necessarily be differentiable. One very simple example that we've done about 10 minutes ago is, can you give me an example of a function being continuous at a point but not differentiable at that point? We only did one problem in this entire class today. The absolute value, right? It is continuous at 0, but it's not differentiable at 0. Bless you. Does this make sense? However, and so this is why I said the theorem is very nice as long as you know how to apply it. What it says is, it says that the function, if you can find a derivative, then it's clearly continuous. Now, how is that actually helping us in real life? Well, that basically says that if your function is not continuous at a point, it certainly won't have a derivative. Does that make sense? Yeah? Okay. So, can you give me an example of continuous function with no derivative? I'm obviously talking about a particular point. So one example is the one we just talked about, which is the absolute value. So if you think about it, think about the fact that it'll look like this. It'll have a sharp turn. It has a corner, a sharp turn, a cusp, or however else you want to call it. Does this make sense? Everybody understands this? Okay. There's also another way of defining a function that in fact is continuous, yet it doesn't have a derivative. And that would be a vertical tangent. And you might ask yourselves, how? Right? Well, f of x equals the cube root of x has a graph that looks like this. As it turns out, my graph doesn't really represent that, but as it turns out, it has a vertical tangent at 0. Okay? Yes?
So that like sine and cosine.
How about them? I mean, what about them?
Would they be like continuous too? Like they have the, I don't know what I'm getting at, just the vertical.
No, as it turns out, cosine and sine, we'll find this out probably on Wednesday, but the derivative of cosine is sine, is negative sine, and the derivative of sine is cosine, which means they're going to be continuous and differentiable everywhere. Because when you take the derivative of one, you end up with the other, and based on the graph, they're continuous everywhere. They're defined everywhere, so they're just going to have, the property everywhere. Tangent, however, is a different story. Right? Just think about the graph of tangent. Okay. Obviously, if a function is discontinuous, then you don't have a derivative, which is basically what I was saying earlier, right? If you have a jump, for instance, you're not going to have a derivative, right? Again, this is where that theorem comes into play and says, if the function is differentiable, then it is continuous, which means if it's not continuous, it can't be differentiable. Okay? All right, let's see. Questions? What would you guess f double prime of x to be? The prime of f prime. Does that make sense? This is called a second derivative. And this is where Leibniz formula comes into play relatively nicely. F double prime of x says I take the derivative of the derivative. Okay? By the way, maybe I should have spent a little time talking about Leibniz notation. Why is this the symbol for derivative? It basically says take the derivative with respect to x. That's basically what this says. That's why it's written in this form. And you might ask yourselves, do I really need the fact that it's in terms of x? And if you're taking Calc 3, then definitely. The key idea is sometimes you look at functions with more than one variable, and so you need to be able to discern between variables. Okay. However, this notation looks a little ugly, and so the way we actually denote things is d squared y divided by dx squared, which basically says you take two derivatives of y, both of them with respect to x. That's, how you would read it. Does this make sense? Okay. How about f triple prime of x?
Is that dx quantity squared or just dx?
Dx squared. So the square is on x. So what would you guess this to be? So we call this the third derivative. Do I need to write this out? Okay, and it's just d cubed y over dx cubed. Usually the standard notation, by the way, the primes, what they actually are Roman numbers. So the fourth derivative is defined to be f 4 of x, and so forth. Now at some point you're going to get really tired of all these Roman numerals, and so if I ask you for the 18th derivative, it might take you a while to write all of them out. And so the convention is, after a certain time, you just write it in parentheses. This is the 18th derivative.
What would you do with
I don't know.
That one.
18 would probably be a stretch. But like for instance, second derivatives come into play very, very, very much. Even third derivatives, for instance in physics, if you have the position function, the first derivative is the velocity, second derivative is the acceleration, third derivative is the jerk. So anyway, okay, let's see. Okay, as far as homework is concerned, what you're going to have is problem 2, which I'm not necessarily going to bother to spend time on, or I don't think I should spend time on. I don't know. Now that I just said this, should I spend time on number 1, which is similar to number 2? You basically look at the graph and you have to identify, based on the graph, if your function's, what is the derivative at a particular point? Do you understand what you need to do? Or you just don't care? You have to basically guesstimate the slope of the tangent at each point. That's basically the idea. Does that make sense? Yeah? Yes? Okay. So then the next set of problems is 18 through 22, which you're given a function, you're supposed to find the derivative and state the domain of the function and its derivative. So it's kind of like what we did with the absolute value function, only that we haven't actually used the definition of the derivative. I used the graphical interpretation of that. So would you like me to do, well, I'm not going to do 17, but would you like me to do like 19, 21, or 23?
That'd be nice.
So actually, now that I said I'm not going to do it, out of curiosity, 17 on page 93. F of x is equal to 1/2 x minus 1/3. Can you tell me what the derivative is? And I want an answer from somebody who hasn't had calculus before. In the sense that I don't want, if you know how to take derivatives of polynomials, if you know what the power rule is, then don't answer this question. Would you know what the derivative is without actually going through the limit? Why not? What about the absolute value of x? How do we come up with the derivative? Well, we can do that, yes. But I would like you to tell me, intuitively speaking, what the derivative is. Yes?
Basically, it's the slope, given that it's just a linear function.
Exactly. Thank you. This is a linear function, right? The tangent of this function is the function itself. Give me any point on the graph, the tangent will be exactly the same as the function, right? That's exactly what argument we used for the absolute value of x, right? And so, that being said, f prime of x is going to be 1/2. Is everybody understanding this? Again, the reason why I asked you not to think about the power rule, because we'll learn next time the power rule that basically just says that, this is going to go away, so we're going to have a half. But that's why I didn't want to. Yes.
So what you're saying is on a linear function, every single point has the same slope.
Well, because your tangent is a linear function.
Yeah.
And your tangent is defined to be a line that touches the graph in one particular point, but doesn't cross it. Well, if it doesn't cross it, the only other way that it's going to touch the graph into one point is it's going to be the actual graph. It's the only line that's not going to cross your original function. Does that make sense? Okay. So that was 17, and obviously, as I said, that was not necessarily that hard. So 19, 21, 23. I don't know. Do you want me to? Bless you. By the way, again, for those of you who actually know calculus, as in, you had it in high school or something like that, and you know the power rule, you know the quotient rule, or anything like that, for these particular problems, for this particular homework, you're supposed to use the definition, which means you're supposed to use the limit. If you don't, then you're basically going to be I wouldn't use that strong of a word, but yes, it's basically say that it would be assumed that you haven't actually solved the problem. Okay? So that being said, you want me to do 19, 21, 23?
Yes.
Which one?
The hardest one.
19 and 21? Okay, so f of x is equal to x cubed minus 3x plus 5. So first of all, what is the domain of f? This should be a hard one. Negative infinity to positive infinity, or all real numbers, right? So f prime is defined to be the limit as h goes to 0 of f of x plus h minus f of x divided by h. So it'll be the limit as h goes to 0 of x plus h quantity cubed minus 3 times x plus h plus 5 minus x cubed plus 3x minus 5 all divided by h. So far so good? So it's the limit as h goes to 0 of x cubed plus 3x squared h plus 3x h squared plus h cubed minus 3x minus 3h plus 5 minus x cubed plus 3x minus 5 all divided by h. X cubes cross out, minus 3x cross out, 5 and minus 5 will cross out. Notice that every single term we're left with has an h in it. And so this is the limit as h goes to 0 of h times the quantity 3x squared plus 3xh plus h squared minus 3, thank you, all divided by h. The h is crossed out, put 0 in for h, and we end up with 3x squared minus 3. Yes?
Do you always use the limit going to 0?
Yes. Remember what the other one said. The other one said the limit as x goes to a of f of x minus f of a divided by x minus a, right? This was the other way of looking at things. The answer here was always in terms of a, which means if you want to find the derivative in general, you would have to take this in terms of a and then just replace the a's with the x's. So it's a little more, I guess, cumbersome. Bless you. Alright, so what is the domain of f prime? Well, it's a second degree equation, right? So we have the same domain, everything. Make sense? Okay. 21. Okay, so f of x is equal to the square root of 1 plus 2x. Well, whatever, it was g of x in the picture over there. What is the domain of f? Negative 1/2 to positive infinity. Does that make sense? Yes? Again, the whole idea is not to guess, right? We have 1 plus 2x greater than or equal to 0. Just work out the algebra and you'll end up with x being bigger than or equal to minus 1/2. Right? Okay. So, what is f prime? The limit as h goes to 0 of the square root of 1 plus 2x plus 2h minus the square root of 1 plus 2x divided by h. Right? Remember, it's f of x plus h, right? So wherever you see x, you replace it with x plus h. So I'll have 2 times the quantity x plus h. That's just 2x plus 2h. Right? Okay, so how do we solve this creature? Multiply by the conjugate. 1 plus 2x plus 2h plus the square root of 1 plus 2x divided by the square root of 1 plus 2x plus 2h plus the square root of 1 plus 2x. So we will have 1 plus 2x plus 2h minus 1 minus 2x divided by h times the quantity square root of 1 plus 2x plus 2h plus the square root of 1 plus 2x. 1 and 2x cancels out. The h's cancel out as well. So I'm left with the limit, as h goes to 0, of 2 divided by the square root of 1 plus 2x plus 2h, plus the square root of 1 plus 2x. Put in 0 for h. I have 2 over the square root of 1 plus 2x, plus the square root of 1 plus 2x. Yeah? Which is just 1 over square root of 1 plus 2x. Well, I have 2 of them. Does this make sense?
If say the number on top was 4,
Then it would be 2 over. Since everybody's wondering, what is the derivative, the domain of the derivative? Not quite, but very close. The domain is minus a half to infinity, but now notice there's a parenthesis in minus a half, not a bracket, because 0 is not a 0 can't be put inside the square root anymore because the square root is in the denominator.
Wait, what?
Before, the domain of f was the same, just 1 minus 1/2 was included, because the square root of 0 is in fact 0. You can have the square root of 0, but you can't have 1 over 0. Okay? And this is one of those instances in which, notice that the domain of f and the domain of f prime are not the same. F prime actually is a little less than f. Okay? Alright, so we'll stop here. I don't know if you're aware of or not. So if you're not aware, maybe I should make you aware. A week from Wednesday, you have your first test.